And we now realize, as a matter of fact, because of quantum field theory, that the difference between something and nothing is not so great as imagined before, because nothing has lots of something in it.
Yeah. Let's speak about that for a moment. When I was younger, I remember questioning the universe, and I couldn't figure out how anything could come from nothing. And that was something that I had asked my brother, who was studying physics at the time. And then he mentioned quantum fluctuations, and I was 8 or so. And then it was approximately at that point that I became an arrogant and inexorable atheist.
Wow. Your brother did God's work, as we say. Go
on. I realized years later that's not an explanation to say vacuum fluctuations.
Sure. Yeah.
But I didn't know that at the time. So because I didn't know, I thought that was an explanation. However, you have now figured out some way of making that indeed an explanation. So can you cover that, please?
How you get something from nothing, you mean?
How the universe can come about from vacuum fluctuations.
Yeah, well, I can give you a summary. As I say, I wrote a whole book about it, so it's kind of... But look, the key aspect of quantum mechanics, which I do talk about in the new book, is that the quantum universe is many things are happening at the same time. And in particular, quantum fluctuations are happening all the time. We can't see them, but quantum systems are constantly fluctuating. And when you combine quantum mechanics and relativity, it's even more exciting, because it says that empty space isn't empty. So the key thing about quantum mechanics, when you combine it with relativity, and I've described this in a number of my books, it implies that empty space isn't empty. It has no real particles, but over time scales that are so short that you can't measure them directly, and this is the uncertainty principle of quantum mechanics, things can happen that you can't see. And in particular, particles can pop into existence that weren't there before, and then pop out of existence in a time scale so short that you can't even see them. Those are called virtual particles. It may sound like counting angels on the head of a pin if you say, well, these particles are there, but you can't see them. Well, we can't see them directly, but what we can do is see their effects indirectly. We know they're there because we have an impact on the atomic energy levels of atoms. They allow us to calculate the atomic energy levels of atoms with an accuracy that's unprecedented in all of science. So we know we have to include the fact that on small scales and small times, particles are popping in and out of existence. It's quantum fluctuations in quantum fields. That's why quantum field theory is relevant. Allow you to produce particles that appear and then disappear. Fine. Well, that's for normal quantum field theory with particles and in space and time. But gravity is a theory of space and time. And so if gravity is a quantum theory, and that's a big if, we don't know for certain, but we have no reason to suspect it isn't, then the variables of that theory, space and time, become quantum mechanical variables. And then space and time can fluctuate. And you can start literally with no space, no time, and then have a little universe with space and time appear and then disappear. Virtual universes can pop in and out of existence. And in quantum gravity, that kind of phenomena happens. But it can happen that if a virtual universe pops into existence with zero total energy, then the laws of quantum mechanics and relativity say that virtual universe, in fact, can be real. It can exist for an arbitrarily long time, and then in order for it to not collapse again, if it say starts expanding and not collapses, certain processes have to happen. But if you asked, what would a universe that was almost 14 billion years old, that spontaneously arose from nothing by quantum mechanical processes, what would it look like today? And the answer is it would look just like the universe we live in. All the properties would be the properties of the universe we live in. Now, that doesn't prove that happened.
Yeah.
But it's strongly suggestive that possibility could explain the existence of our universe. Now, it's all possibilities right now because we don't have a quantum theory of gravity. I said if space and time, if gravity is a quantum theory, and it's a big if. We don't have a theory of quantum gravity. We may, string theory is a good candidate for that, but no one knows if it is a theory of quantum gravity in our universe. And so that's an open question at the forefront of physics, one of the known unknowns, if you wish.
And what's the name of that theory? What you just outlined, which is, okay, look, if you have fluctuating quantum fields and you were to combine general relativity, a fluctuating space-time itself, universes can then, it's just a proposal, a vague proposal, like, or is there a
Well,
name attached to it?
no, I know there's no names attached to it. I propose it. Other people have proposed it, but it's just a consequence, if you wish, of having a quantum theory of gravity. And lots of people have thought about it. Hawking and Hartle and Stephen Hawking's obviously thought about it a lot. I have. Other people have. But it's right now a plausible idea, but it's not yet a complete theory because we do not have a full theory of quantum gravity.
Do you find that when you write books, it helps you clarify your own thinking?
Of course. No, it always does. I mean, that's one of the reasons I write books. That's one of the reasons why I write books. Because, well, there are two reasons. Well, three reasons. One, because I want to repay the favor. When I was younger, it was books about science that got me interested in being a scientist, and it's nice to return that favor. But also, when I write books, you could write the same book over and over again. I know a lot of people who've done that. I won't mention names.
Sure.
But in each book, I try and tackle, things I'm aware of, but try and push those my own boundaries. So it becomes a learning process for me as well. And so it's a combination. Writing a book allows me to study a topic that I might not have the discipline to study otherwise if I don't know it. And if I do think I know it, it allows me to explain it. And many, many times, as you say, I realize I understand things more than I did, or in a different context. Even like, for example, the chapter on consciousness, I had ideas about and biases about about the nature of understanding consciousness, and I found but this forced me to delve into those ideas more carefully and try and even define what consciousness was, which is not the case. Another example is the origin of life. I'd led through through the institute I ran at a university meetings a decade or two ago on the origin of life. And this allowed me to say, well, okay, I understand what those issues are, but what's been happening since then? And what are the key things that are being understood? I mean, long ago, I remember in the first book I ever wrote, which is about dark matter, I was writing about particles called axions. And I was writing about symmetries of nature. And I realized in the context of axions and these symmetries that there was an experiment that gave strong constraints on one symmetry of nature. But I realized in the process of writing it that I absolutely didn't understand it. And I thought I did. I understood what was needed to know. But when I tried to explain it, I realized, hey, there's problems. Now that I think about it, is that really right? And that happens to me in every book I write, and it's fun. It's fun, but it's also fun to learn stuff. And so they're not all books on totally new topics. So I wrote a book on the physics of climate change, which again I've been tutored on over the years, especially as chairman of the board of sponsors of the Bulletin of the Atomic Scientists for a decade. But to go into the detailed history and understanding of climate science, that was a new area. It was also the beginning of the pandemic, so I had nothing else to do. So I was able to do it. But in this book, because it's very broad, it's really all of science, time, space, matter, life, consciousness. There are obviously areas where I knew I'd want to really read up. And again, the consciousness chapter probably
was your favorite.
Probably required the most. Well, I don't know. It's my favorite. No, it was the hardest, which is one of the reasons why I left it to the end. But it was the one where I had to read the most,
right?
Because it was an area where I had a vague understanding, and I'd run some meetings also on nature, on aspects of consciousness. But to really go into it enough to try and say what are the open questions, or to reinforce or invalidate my a priori bias that we don't understand consciousness, I had to really try and see what explanations people gave for consciousness.
If you enjoyed that clip, then the full podcast is out right now. You can click around here. Enjoy. Subscribe to Theories of Everything to get notified of upcoming podcasts, as there are new full-length podcasts every week on the topics of mathematics, physics, consciousness, free will, and AI.